Hi everyone! In this video, we are going to introduce how to graph rational functions. But first, it might be helpful to know what a rational function is, and then hopefully connect it to other functions we have graphed. But first, what is a rational function? A rational function is a function that is a fraction. Let's write that down. But most importantly, within the fraction, it has to have a variable in the denominator. Okay, denominator is the bottom portion of the fraction. So we want to look at the parent function for a rational function, remembering that a parent function is the most basic of that function that we can have. And the most basic fraction we can have with a variable in the denominator is going to be 1 over x. Because 1 is the most basic thing you can have in a fraction, and you're dividing by x, which makes it a rational function. So this is the parent function of a rational. Which you might be wondering, like, what does it look like? What are rational functions going to look like? To which I'm going to pop over to Desmos here. So this is what the graph of y equals 1 over x looks like. This is the parent function for a rational. You'll notice I started plotting points on this function with the table over here. So if you plug in 1 for x, 1 over 1 would be 1. If you plug in 2 for x, you're going to start getting fractions, right? If x is 2, you get 1/2. If x is 3, you get 1/3. Same for the negative numbers. So you'll notice all these y values are like really, really small numbers. And if you kept going up to, like, let's say positive 10, then you would have x be positive 10 and y be 1/10. And those outputs will just get smaller and smaller and smaller, as you see that, guys, right over there. And that's why this graph approaches the x-axis here, because the outputs are getting so small, they're getting really close to 0. But what if you plugged in 0? You'd get 1 divided by 0. Can you take 1 and divide it into 0 parts? No, you cannot. So if you take 1 and divide by 0, the difference between this and every other function we've discussed is you'll get an error as your output, because you cannot take 1 and divide it into 0 parts, which your thing won't graph this, but that's why when x is 0, you'll notice there are no points here where x is 0, or here, right? It never touches 0. It may get close, but you'll see it's never touching x equals 0. So that's one of the defining features of a rational function. Okay, now note if you plug in something like 1/2, you'd get 1 over 1/2. What's 1 divided by 1/2? Think of it as you have one cookie and you divide it into half-size pieces. You would get 2 pieces of the cookie. So 1 over 1/2 is actually 2. 1 over 1/3 is actually 3. Same thing if it was negative 1/2, then it would be negative 2. We can talk about this a little bit more together if you're unsure about how I got this. But as you can see, that gives you more points on the graph. So we have to deal with fractions. That makes this tricky. I understand that, but we'll work at it together and it won't be so bad. So this is what a rational function looks like in general, although we can transform it by moving it, stretching it, all that other stuff like we've looked at other functions. I want everyone to have a graph of the parent function in your notes. So, hey, where'd that come from? I just plotted what this would look like off of Desmos. This is what I want you to plot on your own paper. Pause the video, do that. And as soon as you come back, we'll keep going. Really want to highlight this part here. I didn't have room for it, but that says at 0, you'd have 1 divided by 0. So that's an undefined point. You can't have that happen. It would give you an error. Make a special note of that, and we're going to talk about it later in the video. Okay, now that we've been introduced to this new function, we're going to talk about how you get the key features to be able to sketch a graph. And the good news is a lot of the key features we've already talked about how to find and will not change for this function. So for example, an x-intercept occurs while it's on the x-axis like this, which means it doesn't go up or down at all. So for every x-intercept, the y value will be 0. So if you set the function equal to 0, aka you substitute 0 in for y, we can solve for the x-intercept. Whereas a y-intercept, right, that's going to be on the y-axis like this, which means it doesn't go left or right at all. So every y-intercept will have an x value of 0. Therefore, you can plug in 0 for x, and you can solve for the y-intercept, actually even a little bit easier once you substitute that in. Okay, so now that I've set these up for you, we've talked about x and y-intercepts. I want you to think these through and see if you can solve for y and solve for x to get the actual points. Think about it for a few seconds, and I'll come back with the answer. Okay, if done correctly, the x-intercept is at -1, 0. The y-intercept is at 0, -1/2. For the y-intercept, it's pretty straightforward. You could just look at my work where I clean this up. For the x-intercept, though, you actually need to think this one through. Since we have a fraction, you really need to think about how do you have a fraction and get 0 as the output? So how do you have fraction equal 0? And in order for that to happen, what would need to happen is that the numerator is equal to 0. And then the denominator could be literally any number because 0 divided by anything is 0. And what would you need to plug in for x to make the numerator 0? Well, it'd have to be -1 because -1 plus 1 is going to give you 0. 0 divided by whatever this is going to work, which I'll plug in here just to show you. So if I plug in -1, you'd get -1 plus 1 over -1 minus 2, which gives you 0 over -3, and 0 divided by anything is 0. Okay, so for the x-intercepts, you only really need to look at the numerator part. And for the y-intercept, you just kind of simplify it up here. So I'm going to have us try one more. I want you guys to look at the second example and get your x-intercept here, your y-intercept here, and I'll come back with the answer in a second. Okay, here are the answers to the x and y-intercepts of example 2. It's not so bad because it's in factored form, but remember the x-intercept will come from the numerator because you just want the top to be 0. You could plug in 3 and get 3 minus 3, which is 0. 0 times anything will be 0, right? It's just like polynomials. You can plug in -5. -5 plus 5 is going to be 0. 0 times this will give you an output of 0. So that's why those are your two x-intercepts. Okay, not that the denominator doesn't matter, but the numerator is what needs to be 0 to get an output of 0. And then I plugged in 0 for x to find the y-intercept, cleaned it up. You did get a fraction. It's 15/2. It's totally fine. Just because you get a fraction doesn't mean you did something wrong. So my final answer is 0, 15/2 as I left it as a fraction. Okay. In summary, these are the things you mainly need to know to find x and y-intercepts, is that an x-intercept, the y is 0, a y-intercept, the x is 0, and then just kind of think it through for how you would solve that x-intercept by getting the numerator to be 0. We should even write that. The numerator will have to equal 0 for a rational function because of this idea here, right? To get 0 as an output, you need 0 in the top. So this just gave us a review of how to find x and y-intercepts for a graph, but also introduced us to what a rational function is and then how to apply those skills we already know to this new function. Okay, stay tuned for part 2. That'll help you sketch a little bit more about these functions.